Mr. Bergman, do you know what a diamante poem is?
Diamante. Sounds like two. Di, right? Mono, di, tri.
Yeah.
So diamante. Amante. Sounds kind of French or something.
Well, it looks like...
Two French guys who are eating French fries?
No. It's just shaped like a diamond. The words, when you actually write it out, it's shaped like a diamond. And you've got a certain number of syllables. So anyhow, I have a diamante
about... So how many syllables? How does that work?
So you've got one syllable, then 3, then 5, and then 7, and then 5, and then 3, and then 1. And then
there's like a pattern.
Yeah, and then there's like this transition in the middle of the poem.
Nice.
So I have a diamante about gold.
Gold?
Yes, being the poet that I am now.
You're a poet. You're pretty good at this.
Here we go. Diamante of gold. Okay. Bling. Valuable. Element of kings. I desire you. You must have you. I'll do anything to have you. Why?
Wow.
What did you like?
Well, it sounds kind of selfish. You're looking for gold and you're trying to like be rich.
Well, no, that was the thing. The first time I'm talking about how neat it is, and the transition is how it makes me become obsessed with it.
Oh,
did you see the transition there in the middle?
I missed
it.
I must not be cultured.
No, well.
Hey, now last time, hey guys, we learned about these salts, and we hopefully in class you've learned a little bit more about how to make these reactions work, so that today, as we discuss this on the podcast, you will better understand how to now do the mathematics of this. Now, one thing we do need to talk about that we didn't last time is that when we have those reactions from last time. So, for example, if I have ammonia, I would just add this somewhere like where there's that Ka. If I've got ammonium, this is a reaction from the last time, so you've already written this down, plus water, H2O, and that makes ammonia plus hydronium ions. I wrote that out of order. It doesn't matter. You can then write the Ka value of this, and the Ka would be equal to the concentration of the hydronium. Usually we flip these, and I screwed up. Times the concentration of the ammonia over the concentration of the ammonium, and that's called the Ka. Now, why the A? Because you made hydronium, so this is an acid. So
the ammonium is acting like an acid.
And then conversely, I can then have the other reaction we had, which was HC2H3O2, and dissociating into hydrogens and acetates.
That's not what you want. You
That's
want sodium acetate. Thank
you. I want the C2H3O2 minus plus water, HOH,
there you go,
making the HC2H3O2 plus the hydroxide. And now you can write an expression, the KB, that's a B, equal to the concentration of the acetic acid. It's kind of weird to have an acid in a basic solution.
It's an equilibrium system. That's what you got to keep in mind.
OH negative, divided by the concentration of the C2H3O2 minus.
Right.
So you have a Ka and a Kb.
Problem is you're never going to find a Ka value for ammonium.
Yeah, so here's the gist, is there's always this whole partner concept, right?
Yeah.
So we can say that the Ka of one times the Kb of another is always equal to the Kw.
And one and another are partners. Are the partners, the conjugate acid-base pairs we've been talking about.
And Kw is 1 times 10 to the minus 14. So if the Ka of, say, acetic acid, okay, the Ka of acetic acid is 1.8 times 10 to the minus 5. This is acetic acid, HC2H3O2.
I can look that up on lots of tables.
His partner is C2H3O2 negative.
I can't look the Kb of that up on too many tables.
And then I can find this value because this number times, if you will, x would be equal to 1 times 10 to the minus 14, and you can calculate it. We'll do that in some problems in just a few minutes.
Yeah, so
but it's just the partner. So his partner, his Ka will be multiplied by the Kb will always come out to 1 times 10 to the minus 14th. Or if you think about it, 1 times 10 to the minus 14th divided by the Ka value will give you the Kb value of the partner, of only the partner.
Yep. So let's do an example of one that we have to do that with.
Okay. So speaking of sodium acetate, what is the pH of a 0.140 molar solution of sodium acetate? Well, first we start with sodium acetate. So many students want to do this, NaC2H3O2. Now, what we really care about in the sodium acetate, though, is the acetate.
Because the sodium, we don't care about.
So we're going to write C2H3O2 negative, and we're going to react it with
water.
Water, it's all the water. We must react to the water. Okay.
What was that?
The water. We must react to the water.
I love the mystery accent.
Yes, I don't know what accent it is. By Jove, I do believe we got it. Switch again on you. There.
Yeah.
All right. Yeah.
Still don't know what that is.
I don't either. So HC2H3O2 plus the hydroxide. So this becomes an ice problem because it is a equilibrium reaction. Notice the double arrow. So ICE. We knew we had a
0.140 molar.
0.140. Now you must work in molarities all the time here. And this is 0 and 0. I'm going to ignore the water because of the liquid state of it. 0.140. This will be plus x. Oops, sorry, minus x there, don't I? X plus x and x. So I can say that the K, watch this, the KB, because of the hydroxide up here. The hydroxide up there! Okay.
That's like Pee Wee Herman or
I
something.
was Pee Wee Herman today. Okay, would be equal to x squared.
Woo! You tell this is the fourth one in a row we've done?
Third, isn't it?
Third, sorry, you're right.
Yeah, we've done 3
I can count
in
and
a
do
row.
math really well.
Okay, now, I cannot use the Ka, ladies and gentlemen.
No.
So if you look on the table, let's go back to the table from a long, long time ago. We're going to get message! Oh, I guess somebody just died. Actually, nobody died. People out in Arizona, it is Drive Smart Day at Woodland Park High School. And so whenever that, it's sort of supposed to symbolize a teen
car crash. Every 14 minutes,
dying in a car crash, which is sad.
In a car crash.
So we don't want to build all that.
Don't text and drive.
Don't do that.
And wear your seatbelt.
I didn't know him, but a cyclist was killed that way. Some kid. All right, don't get me started. That was very bad. All right, acetic acid. Acetic acid's Ka value is 1.8 times 10 to the minus 5. His partner is the acetate ion C2H3O2 minus. I don't care about the Ka of acetic acid. I want the Kb of acetate. So what I have to do is find my screen. Is this it?
No, up 2.
There it is. All right.
There.
What I have is that the Kw divided by 1.8 times 10 to the minus 5, and that's the Ka right there, would be equal to the Kb.
Yes.
Mr. Sams, I'm guessing
I have that. Yeah, that is 5.5555555.
5.56. Okay.
Times 10 to the negative 10.
So he calculated this value by just simply plugging it into this equation.
And Kw, if, in case you forget, is 1.0 times 10 to the negative 14.
That is correct. So now I'm going to then take, and now create a screen, 5.56 times 10 to the minus, was it 10?
10.
Would be equal to, what's our concentration?
0.14.
X squared over 0.14 minus x. You now plug it in your solver. Plug it in. Plug it in. Plug it in. We are getting too giddy.
Yeah.
And it's going to be
8.77 times 10 to the negative 6. Getting faster with my solver.
And this is equal to the concentration of the hydrogen. No.
Nope.
This is equal to the concentration of the hydroxide
and
also the
acetate.
Acetic acid.
Yes, acetic acid. You're right. Sorry.
I believe the question asks for the pH.
It does ask for the pH.
So I'm going to find the pOH first. Take the negative log of 8.77 times 10 to the minus 6. Then my trusty calculator friend, Mr. Sams.
You get 5.06.
5.06. Therefore, pH is 14 minus 5.06.
8.94.
So this is the answer.
Now, does that make sense?
Yeah, I don't know. Wait a second. If it makes sense, we should have a base.
Yep.
And since we produced hydroxide,
yes,
it makes it a base.
Basic solutions have pHs greater than 7. Ours was 8 and some change, and so that's greater than 7, so it makes sense.
Yep. Let's quickly chat about this particular diagram. This diagram is very useful in that if you have... Never mind. No, this diagram we will talk about in a minute. Okay, let's do example 2. That comes up after example 3. Okay, what is the pH of a 0.14 emulsion of diethylamine?
Diethylamine.
Now, do I know what diethylamine is? Not off the top of my head, but you know what? We have a table of bases. So if I go back to the table of bases, I have it in blue. I have diethylamine. This one, right?
Yep.
Diethylamine is C2H5NH2. Look, by the way, here is his part which
is
has a
wrong again.
typo.
Yeah.
Mr. Bergman did this. Okay, that should be
I still think it's from the
3.
textbook as a typo.
It certainly could be. This is correct. Let's check them all. I'm just...
The rest of them look good.
yeah, that's the mistake. And, of course, this one is still mistaken. These are the 2 wrong ones. Okay, these are the 2 partners. They're going to need to appear on opposite sides. So we have to write the balanced equation. But we have diethylamine. Is this it? Right?
Yeah.
All right, so we have solution of diethylamine.
Yep. What's the pH?
No, but we'd need diethyl ammonium nitrate.
Yes!
Okay,
That's a bad question. We're going to change the question on the fly right here, guys.
So, sorry about that. We're going to say diethylamine. We're going to say, actually, let's just write it out as an equational way. We'll say C2H5.
In parentheses. 2. NH3 positive.
NH3
plus.
NO3. No, chloride.
Okay, that works too.
All right, so here is our chemical. And I want to know what is the pH of a 0.14 molar solution of this. Now you see I see of the chloride, and this is one large thing. This is sort of like ammonium. Think of this like ammonium chloride. And this is just a big ammonium right here.
Yeah.
Okay? And so when we write our reaction, we're going to say C2H5
Yep.
NH3.
NH3 plus.
Now, I am going to ignore the chloride because this chemical essentially breaks apart into the big uber guy with the positive charge and the chloride.
Chloride never affects pH.
Yeah, chloride, yeah, because it's part of a strong acid.
Yep.
So then I'm going to react it with what?
With water.
With water. I'm going to write water as H2O. And that makes the hydronium ion plus this ugly beast C2H5 NH2. Now we do a nice problem, ICE. So this is very similar to our last problem. We have a point, was it 140?
0.140.
140, and then 0 and 0, again, ignoring the water right here, minus x, 0.140 minus x, plus x, x, plus x, x. So I can say that the K, now watch this, I make hydronium ions. The hydronium is a acid. Acid, 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 acid. So it's going to make a Ka. So the Ka would be equal to x squared over 0.140 minus x. Now I must use the Ka value. So if I go back to my table, we find that the Kb, I'll go back there, that the Kb, if I can find it, is this it?
Yep.
That the Kb, I've said that 14 times because I'm trying to find the screen, is 1.3 times 10 to the minus third. All right, so that's the value from the table. So let's save this for a moment. So remember Ka times Kb equals Kw, and the Kb is 1.3 times 10 to the minus 3. Ka times this is equal to 1.0 times 10 to the minus 14th. You simply solve for Ka, dividing, and you get
7.69 times 10 to the negative 12.
Now we plug this into our solver, and we solve for x, and x is equal
1.04 times 10 to the negative 6.
Hold on, I'm going to write H3O positive, which is
1.04 times 10 to the negative 6.
Times 10 to the minus 6. Now, we did this very quickly. Actually, Mr. Sams was solving the problem while I was talking it through. It is good that you would do the solver problem yourself on your calculator. Put pause and such. Please do that so that you are become Mr. Expert or Ms. Expert solver person. So, now we need to take the negative log of that because we asked for pH, right? So negative log of this value would be about 6.
Yep, 5.98.
5.98. How did I know that? Because 1.0 times 10 to the minus 6 would be pH of 6, and it's just a skosh smaller than that. Okay?
A skosh?
A skosh is just a little bit, yeah. Hey, now we have...
Can you convert that to moles?
I think so. A skosh is equal to...
Can you find it scotial mass? Molar
mass.
scotial? Well, I don't know.
How many have we done in a row? I don't know. Too many. Okay, a little bit of typo. It's not really typo. It's just kind of bad formatting.
Subscripted.
Subscripting. All right, now all we're going to do here, no math. Nope. We're just going to predict. Now, which one has a higher pH? Or is it acidic, basic, or neutral?
Yes.
Which is it? I don't know. Wait. I have ammonium and I have acetate.
Yes.
So ammonium is the partner of who?
Ammonia.
Ammonia. And he is a weak base.
Yes.
Ammonium is a
Weak.
therefore a base.
Conjugate acid.
We'll
of
call
the
him a
base.
conjugate acid. All right, we don't have ammonia.
No. We have
So-
ammonia. Oh.
So that makes him a weak acid, right?
Mm-hmm.
But we also have acetate.
Comes from acetic acid, which is
So-
a weak acid.
So acetate C2H3O2 negative. His partner would be acetic acid, who is a weak acid. So that makes this guy a
Conjugate base.
weak
or weak
base. So if we have a weak base, this is what we actually have mixed together, right?
Yep.
We have a weak base and a weak acid. Who wins?
The one with the bigger K.
The one with the bigger K. So we must look at the K.
Yes.
But we have a tricky question here.
Yes.
We should have probably done this third. Oh well. What is the K of ammonia?
1.8 times 10 to the negative 5.
Negative 5. And the K of acetic acid is
1.8 times 10 to the negative 5.
So what would be the Ka of this? Now actually, Mr. Sams, I wouldn't put it in the calculator.
Okay.
If this is 10 to the minus 5,
Okay.
this ammonium will be roughly about equal to 10 to the minus 9.
Yeah.
Because
Ish.
9 and 5 is 14.
Right.
And the Kb of this one would be about equal to 10 to the minus 9. In fact, they would be the same because these values actually turn out to be the same thing. So, this brings us to a cool chart, okay, which we have a little bit out of order.
Yeah.
Is that, well, maybe not. If the Ka is equal to the Kb, the pH is 7.
Yes. So it's neutral.
So it's neutral. So we have a neutral one here. You'll see we have one of each, I think, in this particular problem set. All right, our second chemical is ammonium cyanide. We'll create a new screen. So if I have ammonium, I like to do this in a chart. Ammonium, and his partner is ammonia. Now we only have ammonium. All right, we only have ammonium, pardon me. This is a weak base. And his K,
1.8.
B, is 10 to the minus 5. We'll just
Okay.
round.
All right.
And then this ammonium is a weak acid, and his Ka is about 10 to the minus 9th, which we just chatted about.
Right.
Our second chemical was cyanide,
Yes.
Cn negative. His partner would be HCN. So he is, HCN, you should know, is a weak acid. We then
Yep.
look up on the weak acid table. Mr. Sams is
6.2 times 10 to the negative 10.
his Ka is about 10 to the minus 10th. Therefore, cyanide's Kb is about 10 to the minus 4th. Now, which is bigger? Now what we're going to compare, the chemicals that we actually
have present.
present are these two chemicals right here.
Yep.
So the Kb is bigger than the Ka.
Yes.
So therefore, if you had a solution of ammonium cyanide, we're not going to try and calculate it. We just want to do it conceptually. Well, the Kb wins. So therefore, this solution would be
Basic.
basic. Do you see how this system works? All right, and we have a third chemical that we want to test, and that would be
aluminum sulfate.
sulfate. You know what? We're going to skip aluminum sulfate. Why would I do aluminum sulfate? Because that makes
Lewis acid.
it's a Lewis acid problem. That's almost a too complex one.
Yeah.
Let's do another one. Let's throw in a different one, and it will be. So let's change that aluminum thing, and let's do ammonium fluoride, NH4F. So the chemicals that you actually have are ammonium. I don't know.
Sounds kind of nasty.
It does. And fluoride's a dangerous chemical. You have
Yeah.
ammonium and fluoride, but we're going to look at who their partner is. Who's the partner of this? We've already done this one. Ammonium's partner is ammonia. Whew. And his K, he's a weak base, and his Ka is 10 to the minus 5. Therefore, he is a weak acid, and his Ka is 10 to the minus 9.
By the way, I don't know if we made this clear, but the exponents are going to add up to minus 14.
Yeah, that's exactly. Yeah. 9 plus 5 is 14. Negative 14.
Right.
Yeah. So the fluoride, his partner is HF. HF is a weak acid.
Mm-hmm.
And a weak acid, his Ka
7.2 times 10 to the negative 4.
negative 4.
So, yeah.
So his K, he'd be a weak base, and his Kb would be equal to about
10 to the negative 10.
10 to the minus 10th. So who wins here?
The ammonium wins.
The ammonium wins. 10 to the minus 9th is bigger. 10 to the minus 9th is bigger than 10 to the minus 10th. So therefore, this substance, the acid, wins. So this would be acidic.
Yes.
So if we go back to our chart here, the Ka wins, and therefore it's acidic. Okay?
There you have it.
That's it. Okay, we have one more big topic to talk about. This is actually pretty simple. Well, it's all conceptual. So all the mathy stuff, just take a deep breath. Take a deep breathe. It's now gone.
No math in this.
No more math. It's a conceptual piece. Okay, now, what happens to acids based upon a couple of things? Now, one of these things, at least in our class, we teach somewhat out of order if you are out in the internet land. We have not spent much time with our AP kids talking about polarity, but they have some background. Okay, what is polar? What does that mean, Mr. Sam?
Polar means it has an end, like a plus end and a minus end for in chemical terms.
It's like a magnet.
Yeah.
Although at a very, very, very tiny scale, because we're looking at chemicals. So if something is the more polar something is, what do you think about it?
More polar, it has more of a plus end, more of a minus end.
I'm going to say more polar equals stronger bonds.
Got it. Wasn't sure what you're getting at there.
Yeah, I know. You don't know what I'm talking about here. Okay, not that you know what I'm saying.
Yeah.
Okay, this is my lecture, and he doesn't know what I'm doing. I'm designing. Okay, so we've got a polarity, and then we also have something called bond strength. Now, bond strength, of course, it sort of makes sense. The stronger the bond,
the weaker the acid.
Yeah, the stronger the bond, the weaker the acid. And so we have a strange thing here is that we have, we're going to look at 4 different acids. We're going to look at HF, HCl, HBr, and HI.
Yeah.
An interesting thing that you need to think about is that actually also the more polar, let's actually write this too, I didn't want to say this. The more polar, the stronger the acid. Because the more chances for it to break apart. So we have a situation. So on this one, we kind of have an interesting thing, is that the more polar let's just do this. More polar equals stronger acid. More chances for it to break up. And also then we'll say this, the weaker the bond equals a stronger acid. So we have both things, we have a problem here. So if we look at HF, because of its polarity, it's the most polar because F is the most electronegative atom on the periodic table. This is the most polar. So this is polar,
so we would
and this is less polar.
Right.
They're still polar.
Right.
You would expect the HF
to be strong.
But you see, because of this bond strength, which is very large, actually unusually large, it makes this weak.
Yeah.
And where these ones, we kind of have intermediate. We have the least polar, but we have a pretty weak bond, so that's why it keeps these 3 acids weak. Okay? Hopefully that kind of clears it up for you. Or as much as mud, I don't know.
Yeah.
More thoughts on that, Mr. Sams?
No, my thought is that the next concept is much easier to understand.
Yeah. How about oxyacids? What's an oxyacid?
Acids that have oxygen in the anion.
So if I have an acid with oxygen, which ones are the strongest? Now, we can actually just look at our table here.
Mm-hmm.
Perchloric acid in HClO4 is a strong acid, therefore has a very large Ka. The next one, HClO3, the Ka is 1.
Still pretty good size.
Yeah, pretty good. This one is 10 to the minus 2.
Yeah,
and
pretty,
this is
pretty large for weak acid,
and
then that one's tiny.
And then we have a second set of acids, the sulfuric and the sulfurous acids, notice. And then the nitric acid and nitrous acid. What do you see as the pattern?
It's looking to me like the more oxygens you have, the stronger the acid.
More O equals stronger acid. That's exactly correct, Mr. Sams. But the big question is, why?
I'm going to say let's look at the structure.
So if I were to draw the structure of HClO4, which I didn't put in the podcast because it was copyrighted, HOClOOO, that's HClO4. This one thing about oxygen. What do you know about oxygen, Mr. Sams?
It's pretty electronegative. Not quite as much as fluorine, but it's right next door.
Yeah, remember on the electronegativity table, fluorine is the top dog, and oxygen is pretty much second place. So what's going to happen is these guys, they love electrons. So electronegative means they love electrons.
No.
And so what's going to happen is the charge center is going to be way over to the right as is drawn on this thing. And that's going to cause this to be a very polar.
Yeah, so that end of the molecule gets to be very negative.
Because there's lots of O's that are pushing the electrons over to the right.
Now, if they're hogging electrons, that bond between the oxygen and the hydrogen gets very weak because the electrons want to go the other direction. They want to go towards all those oxygens. So if those electrons aren't there to make the bond, hydrogen goes, bye-bye, I'm out of here.
Now, if I do, on the opposite end, the HOCl, this is polar, but it's just weakly polar.
Right.
The chlorine in the O, you don't have all these extra O's over here pulling it away.
No.
And so that makes this bond is stronger.
Making it a weaker acid.
Remember, strong bonds make weak acids. Weak bonds make strong acids. So that's kind of that. You may want to read this section. It's pretty cool in your book about the effects of structure on acid-base
And you'll probably
properties.
get one multiple choice question like that on the AP test. That's usually how it shows up.
And probably if you just knew more O's make stronger acid, that's
probably good.
Probably good. And we have just one last topic. I know this is a long pot. Well, it's not that bad.
That's not that bad.
Okay, it's just we've been doing it for too long. Okay, acid-base properties of oxides. We've actually covered this again, but it's just so important to do. You have to be able to write balanced equations with these. If I have a oxide, metal oxides plus water, always make what?
Base.
Base.
Yes. We talked about that with the product prediction lessons, but we're just reinforcing it here.
Pick a metal oxide, Mr. Clemens.
Potassium.
That would be KO, right?
No.
No, why not?
Oxide is -2, potassium +1.
Oh, it would be K2O. All right.
Yeah.
React with water. It makes a base. Now, bases are what? Hydroxides. You must have the hydroxide. So it makes KOH.
2 of them.
And to balance, you have to put 2. Now, wait. While we're at product prediction, is that how you would write that?
No.
You would actually write K2O. Probably they would ask you to have it in solid form. Plus water.
Liquid.
And that would make 2 potassiums, because potassium hydroxide plus 2 hydroxide.
That's a strong base, and strong ones we must write as dissociated on the AP.
That is correct. And if we were to do one more, just for fun on that, what if I had iron 3 oxide?
Iron 3 oxide.
Fe2O3.
Rust.
Yeah, that's rust. We put rust in water. Now, it's not going to happen to some large degree, but you would get a small degree, and you would make FeOH3. And to balance that, I have no idea how to balance
It'd be a mess.
We'll balance it later. No, you could figure it out.
But we would leave that one together because FeOH3 is a weak base, so we do not dissociate it.
Yes,
so we
so
leave it together.
notice I did not dissociate that. And then, of course, the opposite, non-metal oxides plus water makes what?
Acid.
Acid. Classic case of that would be, so for example, I took diphosphorus pentoxide. Diphosphorus pentoxide plus water. What does it make?
Phosphoric acid.
Yeah, and that's H3PO4. That's that one from the long one from the last podcast. H3PO4. How long could that problem be? And I think to balance this, you need a 2.
You need 2.
I think that might maybe in a 3 here, I think. You can go back and look at it. It makes
that's
phosphoric acid. Now, if it had made a strong acid, like let's say you had a reaction. Let's do one of those.
SO3.
Yeah, so let's say we take sulfur trioxide and we react with water. By the way, do not confuse SO3 is not the same thing as SO3 -2. They are not the same.
SO3 is gas. SO3 -2 is an ion. Has extra electrons. It has very different properties.
And this one we essentially just add them together. This one makes H2SO4. But that is actually wrong.
Right.
Because sulfuric acid is a strong acid, so you would write SO3 plus H2O.
This one actually has 2 correct answers.
It's correct. Makes H positive plus sulfate.
2H positive.
2H positive. Or you could actually
write it
H positive plus HSO4 negative, because this is actually a
probably
weak
more
acid.
correct.
This is actually the more correct answer. The second one I'll recopy here.
But either one will get you full credit on the AP test.
Yeah.
And for us too.
Yeah. Okay.
You at Internet Land, ask your teacher.
Well, we have just done 3 podcasts in a row, and we are giddy.
And we're really hungry.
And we're hungry because it's lunchtime. So we are going to eat our lunch. Okay. That's supposed to be a face. This is not working. Okay.
No. You see that big red button, the button with the red stop sign on it?
Yeah, I see it.
We should probably push that one.
You think so?
Yeah, it'd be done.
There we go. That looks like somebody eating something. No?
I have some chili and polenta for lunch.
All right. I have casserole of some kind. Okay, we'll talk to you later. Bye.